Good afternoon. I'm Spot On Weather meteorologist Matthew Euler, and welcome to today's video. This one's going to be on climate factors. I called it climate factors. So I'm going to take an extensive look at climate. Now, climate generically is the average weather at a specific location, the general average weather you would get. On this particular title slide, I'm showing three different types of areas with specific climates. The first image on the left there showing the very dense, broad green vegetation of a tropical rainforest. You can see how very dense that vegetation is. In the middle portion of the slide, I'm showing you an example of a deciduous forest. A lot of deciduous trees. Basically, these trees reside in the middle latitudes and generally tend to go through seasonal changes, especially with what we're familiar with in the fall when the leaves change color and they eventually fall off the trees for the winter season, and then they rebloom again in the summer, or the spring actually, and then everything's really nice and green in the summertime. And then the image on the right shows an example of the Arctic region. Of course, this has been a hot topic of discussion due to the global warming and possible climate change impacts with the acceleration of the changes in the Arctic and what's known as Arctic amplification, where we're warming the Arctic very, very quickly right now. We're having a lot of melting ice glaciers, but we won't get into the topic on global warming just today or the changing global climate. Instead, I'm going to talk to you about the climate factors. What specifically determines the general average weather at a specific location? So let's take a look. I'll start things off with an official scientific definition of climate as well as climatology. So climate, the scientific definition, is to average daily and seasonal weather events for a given region over a long period of time. Now, usually that period of time is considered to be greater than or equal to 30 years. So we look at 30 years of weather data and determining the climate. Now, climatology is the scientific study of climate. And so we do have scientists that are known as climatologists, and their primary role is to look at the climates and to see how those climates have changed over time. And they do so much more important works and research as well. All right, so let's take a look at some of the climatic elements. We look at climatic elements. What do we look at to describe or express the climatic types? Let's start first. We'll talk about moisture, the level of moisture an area receives or has, the amount of humidity in the air. Second is precipitation and clouds, overall cloud cover throughout the course of time. Third would be temperature. And then fourth would be the average wind. Now, when I talk about winds, we talk about average wind directions, how much of the frequency of the time period do we have northerly winds versus southerly winds versus westerly and easterly winds, as well as general wind speeds at specific areas. So let's go right into it. Let's look at climatic controls. Let's go ahead and transition to climatic controls. We'll really get into a discussion on all this stuff as we move along. So the major large-scale climatic controls, the first one we'll talk about is latitude. Now, latitude is the most important climatic control. All right. This controls the amount of incoming solar radiation. Whenever you see the term insolation, if you look at IN in the term insolation, IN stands for is short for incoming. The SOL would be solar, and then ATION, ation, that'd be radiation. So when we talk about insolation, we're talking about incoming solar radiation. So latitude has a very significant role in the amount of incoming solar radiation a specific area receives. Additionally, for latitude, we talk about that being the direct source of energy for weather systems. For example, in the mid-latitudes between 30 degrees north and 60 degrees north, that's where we typically see a lot of changeable weather and storm systems, high pressure systems as well. Latitude also establishes what's known as energy imbalance, as the equatorial areas receive much more incoming solar radiation as compared to outgoing long-wave radiation. So there's more incoming radiation or more energy being received around the equator as compared to the polar areas where we see more outgoing long-wave radiation as opposed to incoming solar radiation. So latitude plays a major role in determining an area's climate or average weather. Additionally, latitude has a significant influence on the temperature of a specific area, where we typically see warmer or higher temperatures the further south you go in the northern hemisphere. If you were in the southern hemisphere, it would be further towards the equator, would be further north in the southern hemisphere. But in general, the closer you get to the equator, it doesn't matter if it's the northern or southern hemisphere, the higher or warmer the temperatures are going to be because of that greater influx of solar radiation. And also, you'll see what's common is the lower temperatures that are in the polar areas, whether it be the South or North Pole. It does not matter. But the greater the increase in the latitude, the colder the temperatures get on average throughout the course of a year. Now, this change in temperature is going to shift with the seasons. Of course, we're very familiar with that living in the United States, where we see much colder temperatures during the winter, much warmer temperatures in the summer, and then you have the transition seasons in spring and fall in the northern hemisphere, in the mid-latitudes, where we will see quite a wide swing in temperatures as transition seasons occur in between the summer and winter months. Latitude also has a significant influence on the moisture. Basically, you'll have higher temperatures, as I mentioned, or warmer temperatures closer to the equator, and greater incoming solar radiation, which results in greater evaporation of moisture from the Earth's surface. And in a lot of cases, this is the ocean surface, where you're getting much more direct solar radiation and towards the closer to the equator, and additionally, higher temperatures have the ability to hold higher amounts of moisture. So the capacity to hold moisture in the air is much greater with the higher temperatures. So equatorward, you're going to have more moisture being held in the air. Now, going poleward in latitude, your temperatures are going to be lower, and that's going to yield less evaporation. Additionally, you have less direct incoming solar radiation the further poleward you get, and that also plays a role in less evaporation of moisture from the Earth's surface. Additionally, colder air does not have the same capacity as warm air. Colder air has a lower capacity or ability to hold moisture. The cooler the temperatures are, the less the air is able to hold the certain specific levels of moisture. And again, this change in moisture shifts with the seasons as well, with the movement of the sun. Latitude also has an influence on the winds. So you can see how important latitude is on climatic areas, on the general climate of an area. So latitude has an influence on winds. Generally, latitude causes global temperature differences to occur, with the hottest temperatures near the equator and the coldest temperatures in the polar areas. So this differential heating, or the difference in temperatures between the equator and the polar areas, this initiates a circulation in the atmosphere. Additionally, there is a circulation that occurs within the ocean as well, thermohaline circulation, but in general, we're talking about the atmosphere, the air from the ground all the way up into the upper reaches of the atmosphere. This differential heating, the hottest temperatures in the equator and the coolest temperatures poleward, results in a temperature gradient, or a change in temperature over a distance. And this initiates what's known as wind, the global wind regime, the global circulation, which is totally controlled by latitude. There's different latitude belts based on the global wind circulations. For example, 0 degrees north to 30 degrees north is influenced generally by easterly wind, and that would be the northeast trade winds. If you go 60 degrees or 30 degrees north, 60 degrees north, now we're in the mid-latitude westerlies belt. That circulation sets up in that latitude belt. And then 60 to 90 degrees, we have the easterly wind component again, the general wind direction from the east, which is the polar easterlies. So the latitude and the temperature differential, the differing amounts of incoming solar radiation, and where your warmest temperatures are at the equator versus the colder temperatures of the poles, gets things moving in the atmosphere, gets that wind flowing, the global circulation going, and creates specific latitude belts. And that determines a lot in as far as the average weather for a specific location. Additionally, when we talk about climatic controls, we need to also talk about these semi-permanent pressure systems. Generally, a semi-permanent pressure system is one that pretty much stays in the same location throughout the course of a year. There are specific seasons of the year in which these semi-permanent pressure systems, whether they be high or low pressure, are stronger and weaker. But in general, a semi-permanent pressure system doesn't move very much. It generally resides in the same location. An example of this would be the Bermuda high pressure system over the western Atlantic Ocean. And with a southerly wind circulation around that Bermuda high, that semi-permanent high, we typically see a very warm and muggy eastern U.S. in the summertime as a high pressure, that semi-permanent high expands. That's just an example of a semi-permanent pressure system. Another example would be the Icelandic low, where an area of low pressure tends to set up semi-permanent low around 60 degrees north latitude, just off the coast of Iceland, and that generally resides throughout the year, being stronger in the winter as compared to summer. So there's just a couple examples of these semi-permanent pressure systems. They do determine the prevailing winds. That's a very important point. Prevailing winds then will influence how much moisture is available. Additionally, the heat transfer mechanisms. Stability is huge when we talk about semi-permanent pressure systems in climate, average weather to location. Stability generally occurs in the west side of a semi-permanent high. The east side of a semi-permanent high is stable conditions. The west side of a semi-permanent high is unstable in the northern hemisphere. And low pressure systems are generally unstable. So stability factors, heat transfer, moisture availability, the prevailing winds setting up their circulation around these semi-permanent pressure systems really makes a difference of what type of weather a location receives throughout the course of time. All right, so let's take a look at some examples of some semi-permanent pressure systems here on the chart here of the United States, and where the stable and unstable air resides in relation to these features. All right. The first thing I'll point out is this cold core high, the very top part of the image, that blue H over Canada. That's an example of a cold core high. On the front side of that high, you may have CP air, continental polar air, very cold and dry air in the wintertime. Even in the summertime, CP air comes down and gives those nice little reprieves from the heat and humidity across the Midwestern U.S., and sometimes in the eastern U.S. But continental polar air, I did a video on air mass source regions. So check out the Spot on Weather video library, and you'll see that. But in general, this cold core high is situated over Canada. There's a couple examples of what are known as warm core highs. When I say warm core, what I mean by that is the warmest temperatures are at the center of the high pressure system. So these two blue H's, the one over the eastern and North Pacific Ocean, and the one over the North Atlantic Ocean, those are your East Pacific high and then your subtropical semi-permanent Bermuda high over the Atlantic. And generally on the east side of high pressure systems, these semi-permanent features, the air is more stable. East sides of highs are stable, while the west sides of these semi-permanent high pressure systems are unstable. And I wish I should have drew the arrows there on the bottom left, pointing from the north to the south, because you generally have a northwesterly flow off the coast of California, clockwise circulation around these semi-permanent highs in the northern hemisphere, so you'd have more stable conditions. You notice you get a lot of fog off the coast of California in the generally throughout the course of the year. Really get a lot of stratiform type clouds on the stable east side of the semi-permanent East Pac high. And then in the eastern United States, again in the summer, the west side of the Bermuda high is very unstable, very muggy air mass with lots of moisture in the atmosphere. And a lot of times when you get a little heating with that moisture in place, you get thunderstorms to pop up daily throughout portions of the southeast, places like Atlanta, Jacksonville, Memphis, into Virginia, Kentucky. You get a lot of pop-up thunderstorms along the Gulf Coast in the summertime because that's the unstable side of the Bermuda semi-permanent high-pressure system. Lows in general, the red L there over Wisconsin in this image, Lows are generally unstable. They're areas in which the air converges and rises in the vertical. As air rises, it cools, and it condenses out and forms these clouds that we see quite frequently throughout the course of the year. And then if we get enough moisture embedded within the cloud, that can go ahead and precipitate out either as rain in the summertime or snow in the wintertime. But those are generally unstable areas that result in rising air motion, while highs are associated with sinking air motion. But here is the position of these semi-permanent pressure systems when I'm talking about the highs over the Atlantic and the Pacific Ocean. Those play a huge role in determining the general climate or average weather of locations, whether we want to look on the West Coast or the East Coast. Another major climatic control will be land-water distribution. This is second to latitude in importance, and the influence on temperature of the land-water distribution is huge. We generally get a larger temperature range over just land areas away from the influence of water, and we'll get a smaller temperature range over the oceans and the coastlines next to the large oceans. Let me show you some examples here in a minute. But first, before I do that, let's take a look at a question. Why do you think England is warmer than North Dakota in winter, even though England is more poleward in latitude? That's a really interesting question. Why is England warmer than North Dakota in winter? It has to do with the location of England surrounded by bodies of water, as compared to North Dakota, which is more continental in its climate, where there's no influence by any major ocean currents or bodies of water nearby. Like I have the bullets above that I just mentioned, you're going to have a larger temperature range over land areas, not only on a daily basis, but also on an annual average temperature basis. And you'll get smaller temperature ranges over the oceans and coastlines. So in this case, England is dominated by a relatively milder ocean current to the west, and the westerly winds blow from west to east in this particular latitude belt, and as a result, the air is modified greatly due to England's location near this source of water. Now, the land-water distribution, what about the influence on moisture? Land areas are generally drier, but have increased shower potential in the summertime. When the land is heated, especially if you get a maritime tropical air mass, very warm and muggy and sticky air, if you get the sun to heat up that land mass, there's a good chance you can get a pop-up thunderstorm and get an area or a brief period of heavy rain showers in the heating of the day during the afternoon or early evening hours. Oceans and coastal areas are much more moist throughout the course of the year, while frozen areas, for example, in the Arctic, where you have a sheet of ice, they're considered very dry. Many people think the climate of the Arctic area, for example, is just very snowy, and they get a lot of snow up there. That's not exactly true. They don't get their annual average precipitation is not as great as you would think. It's just the fact that you constantly see the snow and the ice in the ground, making it seem like it snows a lot there. But in all actuality, that very cold air mass over the Arctic is very dry. In the land-water distribution, what about its impacts on the influence on winds? This land-water distribution, the geographic setup of the continents, is going to disrupt the semi-permanent pressure pattern. That circulation of winds is going to be disrupted. In winter, what does this result in? This results in these thermal highs which develop, these cold core highs. While in summer, you get these thermal lows or heat lows to develop, and they're warmer core lows with the hottest temperatures towards the center. And a good example of this is over the deserts of Southern California. You'll get what's known as a thermal trough to set up, or a heat trough. You get this thermal heat low, and it's just due to the intense heating of the surface. And then you get, on a bigger scale, what's known as monsoons, which there's two types of monsoons. There's a southwest monsoon, which during the warmer time of year in the summer months, the general wind direction blows from the southwest towards Asia, from the Indian Ocean towards Asia, as that Asiatic continent, that landmass is heated greatly. And then you get a northeast monsoon, which is cooler and drier air coming in from the Asian continent towards Indian Ocean in the winter season in the northern hemisphere. So land and water distribution, they tend to disrupt the general circulation, the wind circulation, the global pattern. All right, additionally, large-scale topography, we got to take a look at topography as a major climatic control. Now, topography generally means mountainous or elevated land areas. So when I say topography, I want you to think of mountainous, higher terrain. This actually modifies the other controls. For example, elevation in the form of mountains. When mountain ranges are parallel to the prevailing wind flow, there's little modification or change to the climate. And they tend to act as a natural boundary. An example of a mountain range which is parallel to the prevailing wind flow would be the Alps mountains. So let's take a look at the location of the Alps mountains here geographically. Generally, the Alps are located generally in Central Europe. You can kind of see the circular area there with the Alps over the top of it. Generally north of Italy, parts of Switzerland. You can kind of see where the Alps are located there. Now, they're orientated pretty much west to east. And if you look at that arrow, the MP, the letters MP stands for Maritime Polar Air Mass, which generally comes in off the Atlantic Ocean. And if the wind blows from west to east across Europe, it's generally paralleling, the wind circulation is paralleling the orientation of the Alps. Okay. So with the east-west mountain chain like the Alps, there are not any mountains to take the moisture out of the air mass as it moves into northern Europe. So basically, there's nothing really modifying this particular air mass and changing the climate downwind. All right. Now let's take a look at the Rocky Mountains, on the other hand, of the United States. We still get a maritime polar air mass coming in off the North Pacific Ocean. But the Rocky Mountains, unlike the Alps, the Rocky Mountains are orientated north to south. So here were the Alps, and here are the Rocky Mountains. And you notice the wind circulation, generally the wind blows from west to east in the middle latitudes, between 30 and 60 degrees north. And you get more of a modification. You get the rainier climates and the cooler temperatures on the windward side, and the air sinks on the leeward side where you get the warmer and drier climates. Because of this, the general circulation is disrupted by a perpendicular mountain range, a north-south mountain range, such as the Rocky Mountains. And I did skip this over, so I'll just cover it really quick. Generally, when mountain ranges are perpendicular to the prevailing wind flow, you're going to have much greater modification to the climate or the average weather for a location. And again, the example is these Rocky Mountains. Now, in addition to the Rocky Mountains, I do want to also say that Cascades and the Sierra Nevadas, Cascades are up in the Pacific Northwest in Oregon and Washington states, as well as the Sierra Nevadas down in California. They greatly modify the maritime polar air mass. Now, a maritime polar air mass is pretty much an air mass that comes in off the North Pacific Ocean, and it's generally cool and moist. Now, that moisture is going to be removed on the windward side as air rises at a specific pseudo-adiabatic rate. It's going to result in cooling on the windward side, the development of condensation and clouds on the windward side of these higher mountain peaks. And it's going to cause a lot more precipitation along the west coast of these mountains. So climate along the west coast is greatly modified as this maritime polar air keeps the coast warmer in the winter and cooler during the summer. And as far as those large-scale topography or those mountainous areas, they have a huge influence on temperature. For example, your mean or average annual temperature will decrease or get lower on the windward side. There's less water vapor aloft, and there's more radiation is allowed to escape as compared to the leeward side, where the air sinks and is warmed and it dries out. So a much cooler and moist climate on the windward side of these mountain slopes, much drier and warmer on the lee side. And there it is, pretty much what I just mentioned, the influence of moisture, mountainous areas that are perpendicular to the wind flow. you get increased clouds and precipitation on the windward side, as well as decreased clouds and precipitation on the leeward side. So again, cooler and moist, more precipitation on the windward sides of mountain ranges that are perpendicular to the wind flow, whereas you have much drier and warmer conditions on the leeward side. As far as the mountain's influence on the wind, generally the increased friction as the wind blows up against the mountain, there's going to be some friction that's going to be increased, which is basically resistance to the motion of the wind. It's going to cause the winds to slow down and back. Mountain passes, on the other hand, can cause channeling or funneling winds, something known as the Bernoulli theorem, in which if you constrict the passage or the area between two mountain ranges, for example, if you decrease that surface area, the wind accelerates through the passes. And a great example of that would be the Santa Ana winds in Southern California. When the wind, strong high pressure, sets up over the Great Basin, the clockwise flow around that high directs northeast winds, very gusty winds, as the air accelerates through the openings in the Santa Ana mountains there of Southern California. Here's other examples of great funneling winds as the air basically tries to move through these passes or these openings in the mountains. The Columbia River Gorge is an example, which is just east of Portland, Oregon. That is considered the best place to go windsurfing, in fact, in the world because of the funneling wind effect. Another major large-scale climatic control that I want to mention is the ocean currents. These play a huge role in the climates or the average weather for specific locations. Now, when we talk about ocean currents, we're going to talk about the west coast as well as the east coast. On the west coast, generally we're looking at latitudes between 20 degrees and 40 degrees. On the west coast of continents, in this latitude belt, 20 to 40 degrees latitude are bordered by cold upwelling currents, where there's very small annual and daily temperature ranges. So you're not going to have much of a change between the morning and the afternoon in locations that are bordered by cold upwelling currents. You're not going to have much of a change throughout the course of the year, either on an annual time scale. This area is generally characterized by foggy weather, a little precipitation in the summertime, as these locations are typically in the northern hemisphere. These locations are on the east, stable side of the East Pacific High, that semi-permanent pressure system we mentioned about earlier. In wintertime, the high pressure system, that semi-permanent high, weakens and shifts south, and the jet stream increases in intensity, and you'll see occasional winter storms come in to 20 to 40 degrees latitude on the west coast of the U.S. For example, you can get a lot of rain and snow in California. Now, if I go a little further north in latitude, between 40 and 60 degrees north latitude on the west coast of the continent, it's generally bordered by warm currents, where you'll have cool summers and then mild but wet winters. And there's, again, a small annual and diurnal temperature range because of this. An example of a location like this would be Seattle, Washington. All right. Now, it's not a super warm ocean current offshore. It's still very chilly water. But that warmer current, the relatively warmer current, does modify the air mass as the wind blows over that relatively warmer ocean current. It's going to result in cooler summers and mild but very wet winters, usually in the Pacific Northwest, because of this. Here's a great example of the west coast of the United States. The blue arrows represent the direction of the colder current, and then the red arrow represents a relatively warmer current. And so I'm showing you the general direction. And you get something what's known as upwelling off the coast of California. And basically, as the wind blows away, it blows away from the California coastline. It takes the top layer of that water away from the coast, and cooler subsurface water comes up from below from greater depth to replace that water being taken further seaward away from the California coast. And that's a process known as upwelling. All right. With the cooler California current, what that does, it creates cool summers. Cold upwelling currents are going to enhance the smaller temperature ranges, and there's generally stable conditions for most of the year in places like San Diego and Los Angeles. You don't get a lot of annual precipitation in these locations. You will get fog and the low stratus clouds a lot along the coast in this case. Being in San Diego for a few years, you would see what they call the marine layer, which is that deck of lower stratus clouds that would come in, and eventually throughout the course of the day, it would, in a lot of cases, it would dissipate depending on the strength of the inversion aloft. But in general, you can see a cooler ocean current, that California current off the California coast, which keeps things nice, very pleasant as far as temperature ranges, pretty much year round. The Alaskan current, on the other hand, is more of a warmer current there in the Gulf of Alaska, just off the coast of Juneau, Valdez, and Kodiak. So you kind of see how these ocean currents circulate around the high and low pressure system, the general semi-permanent highs and lows. But all because the Alaskan current is a warm current. It does not mean that the water is warmer than the California current. Just keep that in mind. It's all relative. It just simply means that the water is moving poleward into a colder latitude. And again, between 40 degrees north and 60 degrees north along the U.S. West Coast, you have cool summers with mild and wet winters. Portland and Seattle will be a great example of this. And then between 20 and 40 degrees north latitude along the west coast, you have these colder upwelling currents which enhance the smaller temperature ranges, and there's generally stable conditions on the east side of that semi-permanent high there off the coast of California. Now let's turn our attention to the east coast. The ocean currents impact on the general weather or climate for those locations on the east coast. Now, between 20 and 40 degrees latitude, let's say we're off the east coast of the United States, 20 to 40 degrees north latitude, generally they're going to be bordered by warm ocean currents. Generally warm year-round. There's a moderate annual temperature range, so it's not exactly small, but it's not extensive or very significant annual temperature change or range. It's frequent showery precipitation at this particular locations, 20 to 40 degrees north latitude on the east coast. Now, if I go a little further north on the east coast to 40 to 60 degrees north latitude, I'm generally bordered by colder ocean currents with a larger annual temperature range, very cold winters, and cool summers. So let's take a look at the ocean currents off the east coast of the United States. All right. So coming down from the northeast, the blue arrow there off of New England, Boston, and just off of New York, that is an example of a colder ocean current known as a Labrador current. While the red arrow there off the southeast coast is known as the Gulf Stream current. That red arrow is that Gulf Stream current is a very warm current, while the Labrador current is a cooler current. So if I'm between 20 and 40 degrees north latitude, places like Jacksonville, Florida, Charleston, South Carolina, locations like that. Norfolk, Virginia is in there. Just in general, the warm currents keep the land warm year-round. We have very unstable conditions, showery precipitation, and a moderate temperature range prevails throughout the course of the year. Whereas if I go a little further north, the 40 to 60 degrees north latitude, I'm influenced more by that colder Labrador current off the east coast, which has less effect on the modification of the landmass. So you get a larger annual temperature range and very cold winters and cool summers along places in Maine, Massachusetts, Rhode Island, all the way over to Connecticut, Long Island. This is a case where you get north of 40 degrees north latitude, and now you're talking about some of the latitude effects, kind of trumping the ocean effects in a lot of cases. Right. In addition to the major climatic controls, we have other smaller scale climatic controls as well. Lakes, such as the Great Lakes as an example, or any large lakes like the Great Salt Lake. The lee side of the lake is greatly modified. So the lee side is generally that side that is downwind of the direction from which the wind is blowing. The general lakes must be unfrozen to affect the climate. So, for example, in the wintertime, in a lot of cases when the Great Lakes freeze over and they become a sheet of ice, it's basically like a sheet of land at that point. They just don't have much effect on climate if they're frozen. But if they're unfrozen, they will have an effect on climate. The influence of lakes on temperature generally produces a moderate temperature range, both diurnally on a daily basis as well as annually. And the influence on temperature delays the onset of summer and winter, really. As far as moisture, this is huge. This is a huge small-scale climatic control, especially on unfrozen lakes in the wintertime. Downwind of the Great Lakes, for example, places like Erie, Pennsylvania, Buffalo, New York, Syracuse, New York. You generally get increased clouds and precipitation on the leeward side in those areas that I mentioned. If the wind's blowing across an unfrozen Great Lake body of water, this is where you get the lake effect snow belts, or we call it the lake effect snow machine, where incredible amounts of snow fall on the leeward side of the Great Lakes. And generally, the effect of moisture, it ranges between 20 and 30 miles downwind or on the leeward side. You may have clouds extending up to 100 to 150 miles on the leeward side of these Great Lakes. In wintertime, what do the larger lakes do? They tend to intensify low pressure systems. In the summertime, the Great Lakes may trigger convection due to lake breezes. All right, and an influence on wind. A warmer lake is generally going to be associated with a land breeze, and then a warmer landmass, more of a lake breeze. So, for example, during the daytime when the landmass heats up much more efficiently and quickly as compared to the nearby water of the lake, the air is going to rise over that heated landmass, and air is going to come in from the lake towards the land, creating a lake breeze. And this can keep temperatures nice and cool, and this happens a lot in locations such as Chicago. If you get a northeasterly wind coming in off of Lake Michigan during the summertime, you can actually have a cooler area close to Lake Michigan, cooler temperatures due to that lake breeze. Generally, at nighttime, the pattern of circulation reverses to where the lake is now warmer, the land cools off much more efficiently, and you get what's known as a land breeze, where the wind shifts direction from the land towards the lake. And then other small-scale climatic controls I must mention are human activities, what we decide to do, our choices we make. Increasing or decreasing vegetation or trees can affect the climate. For example, the thinning of the rainforest in the Amazon Valley, changes in topography, whether we have volcanoes involved. Volcanoes will spew out a lot of sulfur dioxide. If the volcano is explosive enough, it can actually send gases and aerosols all the way up into the upper troposphere and lower stratosphere. And that debris from the volcanic eruption, those gases can actually act to block out the sun, resulting in a cooling climate. An example of this would be right after Mount Pinatubo erupted in 1991 in the Philippines. Take a look at that sometime. It's real interesting. Go ahead and Google Mount Pinatubo and look at the eruption in 1991, and then look at the temperatures after that eruption. And that shows you the impacts of explosive volcanoes and those aerosols and gases, sulfur dioxide, kind of acting as a layer to block out the sun's incoming solar radiation and resulting in a cooler period of time. Pollutants also, I find this really interesting. Right now we're in the midst of this coronavirus pandemic, and just looking at the maps in China and Europe and even the United States, what the stay-at-home and the shutdown and disruption to our normal lives, what that's done to the amount of pollutants being produced in the atmosphere from our factories and from our vehicles, the carbon emissions, all decreasing drastically during this pandemic. And so, yes, pollutants can have a huge role with our human activities and what we decide to do on a daily basis, how many cars are on the road. And then finally, to end this training on the climate factors, I'm going to talk about how climates are classified. The general basic method is latitudinal. So again, latitude being the most favorable climatic control. This considers temperature and sunshine distribution only when I do this via latitudinal method. The 5 main zones are we have one tropical zone, which is warm year-round. We have 2 polar zones, which are cold year-round. And then we have the 2 temperate zones, which contains the characteristics of both extremes, the heat and the cold. So generally, this is the way we divide up these 5 main zones, considering both the temperature and the sunshine distribution. Additionally, there's other systems in place, which include precipitation. One of the more well-known ones is the Köppen classification, climate classification, which he recognized 5 groups of climate that corresponded with 5 vegetation groups. We have to take a look at the types of vegetation we have in specific zones, because that really makes a difference in what type of climate we might see based on the annual precipitation that's received at those locations. The Trewartha one, that classification system is a regional distribution of climates. And then you have Thorn weights, which is a developed method for computing potential evapotranspiration by using air temperature alone. Now, evapotranspiration is the evaporation of moisture from plants, from the leaves, and from the stems and the roots. All that, the sun heats the plants. If they're wet, it's going to result in moisture being evaporated off the plant. And that's what evapotranspiration refers to. All right, so that wraps things up today on discussion on the climate factors. Climate is generally the average weather in a location. If you ever plan a trip on going somewhere, you usually want to look at, hey, what type of weather do they normally get there at this time of year? So that really, climate plays a large role into how you prepare for your trips, whether you're going on vacation, your destinations. You don't want to be surprised. There's been people I know that go out to San Francisco in the summertime, and they're thinking, it's summer, it's warm, it's California. And what a surprise and a shock they get when they get out there and it's freezing, because you have a colder California upwelling current off of San Francisco, and you get a strong wind in off the Pacific Ocean into San Francisco. And so it's actually pretty chilly in San Francisco during the summer months. So climate plays a large role in our decision-making, how we pack our luggage and for our trips, and just in our daily lives. So we covered terminology, the difference between climate and climatology today. We took a look at the major large-scale climatic controls, the latitude, the mountain distribution, whether it's a perpendicular or parallel mountain range. We looked at ocean currents as a major control. So we did take a look at some major controls there. Smaller scale climatic controls. Again, we're getting back to the lakes, the impacts of lakes on climates, whether you're on the lee side or downwind of the lake, where you're located, or whether you're upwind of the lake. Additionally, volcanoes, human activities, how we basically live, whether we decide to increase or decrease vegetation, as well as the amount of pollutants we throw in the air, which act to trap heat. And then we looked at the classifying climates briefly. We looked at the basic method of classifying climates is via latitudinal methods, considering temperature and sunshine distribution only in these 5 main zones. One tropical, where it's warm year-round. Then you have 2 polar zones, which is cold year-round, and then 2 temperate zones, which is kind of in between the warm and the cold. And then we looked at Köppen, Trewartha's, and Thornweight's climate classification, which that also includes precipitation. All right, that wraps things up today on the video at Spot on Weather. Just want to share this with everybody, where to find us on social media. We have Facebook, the Spot on Weather page. We also have Instagram. We're also on Twitter, and we're also on the Spot on Weather Weebly website. Now, the Spot on Weather Weebly site, I recently have updated with some awesome photographs of the sky, different cloud features. I cover a wide range of weather across Southeast Virginia, and you're really going to love some of the photos I posted on the Spot on Weather Weebly page. In addition, I try to keep up to date a daily weather map, as well as occasionally I'll do a 7-day weather forecast, as well as the latest synoptic discussion from the National Weather Service. But if you need more updates on weather that pops up in your neighborhood, subscribe to Spot on Weather for the most accurate weather forecasts. Obviously, we're on the YouTube channel, We really hope you enjoy these videos, and I wish everybody great health as we continue to move forward with the coronavirus pandemic. Please be safe. Wish the best for you and all your families out there. All right, that wraps things up today at Spot on Weather. I wish you nothing but the best. God bless everybody. Until the next video, take care.